Good afternoon, participants. We're just waiting for the resource person to join. We'll start immediately after that. Thank you.
Hello.
Yes?
Yeah, this is Dr. Lalit.
Yeah, sure, sir. We'll just make you co-host and then we will start.
Sure.
Good afternoon, everyone. It gives me great pleasure to have Dr. Lalit Singh in today's afternoon session. I will start with the resource person's bio and then I will hand it over to Dr. Singh. Dr. Lalit Kumar Singh received his PhD degree from Indian Institute of Technology, Banaras Hindu University at that time. He is currently a scientist in NPCIL BARC, Department of Atomic Energy, Government of India since 20 years and has had distinction of working on pressurized heavy water reactors and light water reactors. He has an illustrious career and succeeded in several critical jobs assigned to him in his illustrious career, though each of them was challenging. His assignments over the years range from design, development, testing, related research and site validation of the safety critical computer-based systems of Indian nuclear power plants. He has published several research papers in journals of high impact factor like IEEE Transactions, IEEE Computer, ACM, etc. He has been invited for chief guest, keynote speeches, session chair, and talks in many international conferences and short-term courses, workshops, and FTP programs from many IITs, NITs, and other institutes of national importance. He is a recipient of many awards like Publication Award, Group Achievement Award, etc. He is a reviewer of several SCI index journals of high impact factor. He is a life member of Indian Nuclear Society. He is a founder member and industrial coordinator of the proposed Center of Dependability at IIT DHU. He is in the panel of Faculty Assessment Committee for Department of CSC IIT Roorkee to assess their research profile and give recommendations. He is a member of editorial board of many reputed journal and guest lead editor of many special issues. He is supervising many PhD students of different IITs, NITs, and is PhD thesis examiner of IITs, NITs, and other reputed institutes. He is an expert member of Industrial Policy Formation of IIT Ropar, BOS of many autonomous institutes, and member on the advisory board of many institutes and universities. He is a reviewer and project collaborator of research proposals of Board of Research in Nuclear Science, BRNS. He is also faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France, etc. for importing nuclear reactors that are based on new technologies. His research interests are in the area of reliability, safety, and security of safety critical computer-based systems. So far, he has completed 33 projects of Department of Atomic Energy, Government of India. We are very pleased to have Dr. Lalit Singh here. I kindly request him to take over. Thank you.
Yeah, thank you, Dr. Raghuram, for introduction, and I would also like to thank to all the organizing committee members who has provided me this opportunity to share some of the research experience. So just let me share my slides to start with. So I hope the slides are visible and it is changing also. Can you please let me know?
Yes, sir. It's visible and I can see it change.
Yeah, thank you. So I'll be talking on machine learning for reliability analysis of safety critical systems. So before going to the topic, I'll be more interested in letting you know the importance of this topic, and so that I can create a motivation. What is the essentiality of this topic? So when I say like safety critical systems, these are the systems, the failure of which can lead to the catastrophic disasters or even it can lead to the loss of human life. And there are various applications where safety critical applications, for example, the aerospace, the nuclear energy, the defense, the space, automobiles, where we use the safety critical systems, and because of its safety significance, these systems must be reliable, must be highly reliable, and hence there should be a technique where we can perform the reliability analysis of such safety critical systems. Reliability analysis means like quantitative as well as qualitative. So this presentation will be discussing the quantitative reliability analysis of these safety critical systems, and we'll be seeing like how we can make the use of the machine learning, because if we talk about the reliability, it depends on the statistical data and how we can make the use of them. So if I talk about the reliability, what does reliability mean? So as per the definition, the reliability of the system is the probability of the failure free of the system up to a given period of time under certain environmental conditions. Now, this definition is very important, and each and every term we need to understand. First, I said it is a probability. So, definitely, if I'm talking with respect to the quantification of reliability, its value ranges from 0 to 1. And 0 means it is least reliable or no reliable at all, and 1 means it's the highest reliable. And I said it's a probability of failure free operation. Failure free operation means success operation, and up to given period of time. Now here, up to what period of time you are talking about, that is important. I cannot say like its reliability is this. I'll have to tell up to what period of time you are talking about, because nothing is reliable for infinite period of time. And this time is known as the target time basically. And then I say, and this is also very well, if you want to correlate it with the real scenario, uh, that nothing is reliable for the infinite period of time. You can memorize your childhood days where you must be having many friends, and you would be thinking like these friends are going to be forever. But as and when you grow up and your priority gets changes, your interest gets changes, and it may be possible like the uh, older friends are being replaced by the newer friends. So uh, it means you have to here the time is very important, up to what period of time you are talking about. And next, I said under the stated operating conditions, it is very important because the reliability of any product depends on the operating conditions. So one product can be very much reliable under one operating conditions, and the same product may be less reliable in other operating conditions. So you have to very much you have to also consider the operating conditions. For example, suppose I go to purchase a refrigerator, and it gives a warranty period of 1 year, and when I come back uh, with the refrigerator and to home, and suppose if I throw it from 14-story building, then it can collapse, and then I cannot go back to the vendor and say, look, you have given the warranty period of 1 year. I want the replacement of this product. What he will say, like you have not, followed the operating conditions under which this product was supposed to be operated, and hence your warranty has been voided. So one thing I can conclude here is reliability is a function of time as well as under which operating conditions you are running your or operating your product. So to start with, let me go through the today's outline quickly. We'll be discussing, we'll see the introduction to the reliability, although we have already discussed, but we can see how mathematically we can represent the reliability, because we are more interested in the quantitative analysis, and hence we have to understand the mathematical fundamentals. Uh, then I'll be discussing on battery nets and modeling of the system. So battery net, it is basically a mathematical formalism, and this is a graphical tool also, and the concept was introduced by C.A. Petri, who was a PhD scholar, who was a German PhD scholar in 1960s. And he introduced this modeling technique to model the stochastic processes. So if you want, if you categorize the processes, it can be broadly categorized into two types. One is the stochastic process, and second one is the deterministic process. So deterministic processes are those processes, the outcome of which can be 100% guaranteed. For example, suppose I do have a pen in my hand, and if I drop down the pen, I can 100% guarantee it is going to fall down because of the gravitational force that is acting on it. And while the stochastic processes are those processes, the outcome of which cannot be 100% guaranteed. In spite of systematic planning. For example, suppose I need to catch a flight for Hyderabad to attend a meeting at 5 p.m. And considering all the local traffic delays, suppose I start here from Bombay, for example, at 12 a.m. to catch my flight at 2 p.m. And I have considered all the local traffic conditions as well as the worst scenarios like flight delays and some overhead also I have taken. But then also there is a probability that I may miss my target. And the reason could be manifold. The reason could be probably the normal route that goes from my place to the airport. Some road construction is going on, and where I came to know after I travel like 15 kilometers, and then I'll have to traverse back and have to take the alternative path, which is quite long and which is very much deviated also. Or the other reasons could be there could be the flight cancellation because of some technical or administrative reasons, or excessive flight delay can also be possible. Or there may be some local traffic conditions at Hyderabad also. So I mean to say, in spite of rigorous planning or systematic planning, I may miss my target, and hence there is some randomness in the system. So randomness means the things which is unknown to me in advance. It is known as randomness. So uh, to capture such kind of systems or stochastic processes, this battery net modeling technique is very suitable, and it is a mathematical tool because we can embed some mathematical language to or knowledge into this tool to compute some of the important variables to know more and more insights about the system. So we'll be seeing what is the basic building block of PetriNet with the help of and working mechanism with the help of one small example, and then we'll be definitely taking a case study where I can model that case study using PetriNet.
Can we interrupt Dr. Lalit? Sorry for the interruption.
Yeah, please, madam.
Sir, I think the slides are not moving.
I'm now right now I'm in the outline slide. Is it?
Yeah, your agenda of
Yeah.
six six.
Yeah. So please listen to me. You will
Oh
come to
yes.
know. Then only you will be able to synchronize the slides and my wordings. Okay.
Thank you. Thank you.
Yeah.
Sorry.
So and then I will be discussing the properties of the Petri nets and what are the analysis techniques. And thereafter, I'll be introducing the reliability prediction framework where I'll be discussing the various phases that should be involved in predicting the reliability. And I will be also discussing what are the various activities in each of the phase by taking a real case study, and then we can conclude our session. So background this I have discussed. Now let us see some mathematical representation of the reliability. So suppose let x be a random variable that represents the time to failure of a component. It means my component should work up to that period of time which I can assign to that random variable. And if it is failing before this time, I will consider that my component is failed. So it should work at least up to the target period of time. So the reliability of the component at time t is given by Rxt. As I said, it is a function of time. It will be equal to probability that that random variable, the value of that random variable will always be greater than t, because your target time is t and you want your component to function at least up to that target time. And from the total probability law, I can equate it as 1 minus probability x is less than is equal to t. And where x is less than is equal to t means your product has been failed or your component is failed before time t, and hence it is a failure probability, which can be denoted by fxt, which is also a function of time. So the failure probability, we can also name it as unreliability. So the reliability is equal to 1 minus unreliability, and that also comes from the total probability law. Now let us go through some of the traditional methods that are being used for quantitative computation of quantitative analysis of reliability. So one of the prominent model is known as reliability block diagram, which is a series parallel reliability block diagram, and it represents the logical structure of a system with regard to how the reliability of its component affects the system reliability. Now suppose, so basically it is a logical structure, means it basically depicts the architecture of the system. For example, if I take the laptop as a system, so the components could be the screen, could be buttons, could be ICs, could be the connector, could be the wire, uh, could be the mouse, could be capacitors, could be motherboard, could be hard disk, and so many other components, and how those components are basically arranged. And if we are able to assign the reliability of these basic components, which can be taken from the statistical data or the logbooks which are available on the internet for electronic components or for mechanical components. So those logbooks are basically internationally recommended and has been made from the international experience. And then if your components are in series, you can use the formula of the series reliability to compute the reliability of the overall system. For example, if your system contains only two components, C1 and C2, having the reliability R1 and R2, then the reliability of the totals of the overall system will be R1 into R2 if those components are in series. So we have to then apply the series reliability formula. Otherwise, if they are arranged in the parallel, you have to apply the parallel reliability formula. And in this way, we can compute the reliability of the overall system. Now, coming to the next modeling technique known as the reliability graph, which is also similar to the reliability block diagram, but having a different building blocks that consist of nodes and arcs. And nodes are used to model the link between two components, and arcs are used to model the component itself in the system. For example, uh, if you are able to see this figure, the left figure represents the reliability graph where all the vertices A, B, C, D, these represents the connectors of the components or the links between the components, and all the V's, that is the vertices V1, V2 up to V4, they represent the component itself. And hence, in this way, the reliability graph can be transformed equivalently into the reliability block diagram, which is shown in the right figure. So you can see all the V's have been replaced by the component itself, and all the vertices has been replaced by the connectors. And now you can see like these components I1 and 4, these are in series, so you can apply the series reliability formula. For example, their reliabilities, the component reliabilities are R1, R2 up to R5. And so the reliability of this segment of 1 and 4, which are in series, can be R1 into R4. Similarly, of 2 and 5 will be R2 into R5 because these are in series, and then all the three segments will be in parallel, and you can use the parallel reliability formula. Now, one more important traditional methods
No.
that are basically that is being used in the safety critical industry, that is known as a fault tree, which represent all the sequences of individual component failures that cause the system to stop functioning. And it is a tree-like structure. So ultimately, in the fault tree, what you do, you have to first observe the failure. For example, if I say laptop has been failed or my laptop is not working, so it is a failure observation. Then you have to keep on deducing the root causes or the causes that till I reach to the root causes. For example, if I say my laptop is not working, the reason could be electrical failure, mechanical failure, or electronics failure. For example, what is a mechanical failure? Then I'll have to deduce further. Mechanical failure could be break in the screen or break or uh, power button fail to push, or keyboards button fail to push, or whatever. These could be the mechanical failure, for example. And if those then if those basic events are because that has to be connected with the AND logic or AND gates and OR gate. If those basic events are following AND logic, they have to be connected by AND gate. And if they are following the OR logic, they have to be connected by the OR gates. And if they are connecting with the or they are connected with the AND logic, you have to multiply all the basic failure probabilities of those root causes of those events, basic events, and then it will come out. It will give the failure probability of the top event, and in this way, and if those events are arranged in the OR logic, you have to add those basic probabilities, and in this way we can keep on traversing the tree till we reach to the top event, which denotes or which represents the failure probability of your system, of my laptop. And then if I subtract it by 1, it will give the reliability of my laptop, because we have already seen reliability is equal to 1 minus failure probability. So anyways, the models that we have looked so far can be solved using fast algorithms, but they assumes the stochastic independence between the system components. But in the real scenario, if you look into the real industry systems, one component may fail because of the other component, because of the wrong input getting from the other components. And this stochastic dependence, it is essential to capture for accurate measurement. And for that there are the several stochastic modeling technique were introduced. For example, the Markov model or the Petri nets. So if you see the Markov models, these are the most powerful tools for reliability and safety analysis because they can provide the modeling capabilities for all sort of independencies, and they have the potential to model all the complex interactions inside the system. And it has a capability to depict the stochastic process. If you see the basic construct of the Markov chain, it basically contains the set of states and set of the transitions between those states. So ultimately, the idea was you can treat any system composed of the various states. For example, if suppose human in the system, the various states could be running, walking, talking, laughing, and one state can transit to another state. And these states can be categorized into two types, can be behavioral states or can be failure states. And behavioral states are the normal states. For example, as I said, eating, laughing, talking, walking. But failure states are, for example, if anybody is meeting an accident, it is a failure state. So a good idea is to find the reliability of the system if you are able to find the probability of that system being in all the success states, and you can sum up those probabilities. That will give the quantification of the reliability. Or the other way out, because the failure states are very less as compared to the behavioral states, you can sum up all the failure state probabilities and then you can subtract it by 1 to give the quantification of the reliability of the overall system. Now let us see some of the mathematical concepts which we are going to use in our prediction framework that I will be introducing afterwards. So suppose there are the two states I and j in a system, and let Qij represents the transition rate from one state to from state I to state j. And transition rate means number of transitions per unit time. Then I can define the transition rate from one state to the same state is equal to minus sum of all the transition rate from that state to rest of the states other than self state. And this equation is very important. You need to remember which we are going to use. And the other term that I want to define here is generator matrix, or the transition matrix. And as the name says, the transition matrix, it is a matrix where you can write the rows and the columns, all the states of that system, and you can fill in that matrix elements where you can fill in the transition rate from one state to rest of the states. And in this, the generated matrix will be known as transition rate matrix or generator matrix. Now coming to the Petri nets, which as I said, it is a graphical and a mathematical tool. And Uh, uh, so let us look, we have already discussed about the Patrinet. So let us look some of the important milestone by which the Patrinet has become so popular. So as I said, the concept was introduced by C.A. Petri in 1962 by who was a German PhD scholar, and he introduced this concept to uh, model the stochastic behavior of the processes. And after going through the thesis, the researchers were very influenced, and they were thinking if this modeling construct can be used to model the concurrent systems or the parallel systems. And with this objective, they MIT USA conducted a conference on concurrent systems and parallel computation in 1970. And then the conclusions were very fruitful, and the people were more eager to know the related methods and whether the modeling capability of the models can be increased, of that particular model can be increased. And with this objective, again, they decided to meet after 5 years. So in 1975, again, MIT USA conducted a conference on Patrinets and related methods. And the conclusions again were very fruitful, and it started gaining popularity in the industries. So looking at the demand on the industries, Germany started a course on general net theory of processes and systems, where the people could be able to learn the modeling techniques. And then the people from different domains were also interested to explore the potential of this model, whether it can be used for their particular kind of applications. And with this objective in 1980, the first European workshop on applications and theory of patronage were conducted in France. Then researchers were coming out with a different flavor of patronage. For example, if I want to work on the real-time systems, definitely the timing information plays a very important role. So a flavored patronage known as timed patronage, where I can embed the timing information, uh, uh, for which the first international workshop was conducted in 1985. So, and in this way, there are other flavors of the Patrinet also. So, although this is not an exhaustive list, but it gives a motivation of this Patrinet, and it discusses the important milestone which has been achieved by this modeling technique. And if you look into the applications, it has a potential to cater almost all kind of applications. Now let us go through the Patrinet working mechanism and how we can model the things with the help of the Patrinet. So to start with, suppose I want to model a very small chemical reaction which you might have studied in your, 10th or 12th or 10th or 9th. That is hydrogen plus oxygen that gives water. And suppose I want to model this chemical reaction. So before going to the modeling model, I would like to discuss the basic building blocks of the Patrinet. So the figure that you are able to see, it basically represents the model. The left hand side model, the left hand side of this equation, the model of the left hand side of this equation, that is 2H2 plus O2. So let me first start with the basic building blocks of the Patrinet. So if you are able to see, there are the three big circles, and these big circles are known as places. So there are the three places, and I'm representing these, I'm using these places to represent one for hydrogen, one for oxygen, and one for water. Then you are able to see a rectangular bar. Uh, there is only one rectangular bar in this figure, which is known as transition. And so the places can be connected with the transitions, and transitions can be connected with the places. but there cannot be direct connections between transitions and places. Now there is a concept of input so this is uh, so the connections are through the directed arcs. So there are the three directed arcs, if you are able to see in this figure. One is connecting hydrogen place to transition T, one is oxygen to transition T, and one is transition T to water place. Now next, there is a numeric number that is assigned on each of the transition, on each of the directed arc. And for example, the arc that is connecting hydrogen place and transition T is having weight 2. And the arc which is connecting oxygen place and transition T, I have not put any numeric number. So by default, it will be treated as 1, or you can explicitly put numeric number 1. Similarly, the weight of the arc that is connecting transition T and water is 2. Now, the next is one more building block that is, so this numeric number is known as weight. I will discuss the significance of this when I will be discussing the working mechanism. Then you are able to see there are the embedded circles inside the places, and so for example, hydrogen place contain 2 embedded circles, and I'm representing, and these embedded circles are known as tokens. So I have taken 2 tokens in the hydrogen to represent 2 atoms, because hydrogen contains 2 atoms. Similarly, oxygen contains 2 atoms and water contains 0 atom. For example, I have not considered here. The reason I'll tell is in a while. And this the state of the system basically is represented by the distribution of the tokens among the places. So if you are able to see in this figure, the distribution of the token are 2, 2, 0. So, and it represents the initial state. It means the left side of this equation, that is 2H2 plus O2. And now I have to convert it into the water. So it means I need to change the state of the system. And for changing the state of the system, I have to change the distribution of the system, but there is a rule by which the distribution of the system can be changed. And the rule says that at least one transition in the Petri net figure must be in enabled state. So here, because there is only one transition, it should be in enabled state if I want to change into the water. And but there is an enabling criteria of the transition, and which says that all the input places must contain sufficient number of tokens. So you can see the input places of these transitions are hydrogen and water, or sorry, hydrogen and oxygen place, and these places must contain sufficient number of tokens. But what is the sufficiency criteria of the token? And here the significance of the weight comes into the picture. So it will be decided by the weight of the respective arc. So you are able to see the weight of the arc that is connecting hydrogen place and transition T is 2. So hydrogen place must contain at least 2 number of tokens. Similarly, oxygen place must contain at least 1 number of tokens. So here the eligibility criteria fulfills, and hence T is an enabled condition. And when T is in enabled condition, it fires. And when it fires, the token moves from the input places to the output places. But how many tokens will be moved out from the input places and how many will be deposited to the output places? That will be totally governed by the weight of the respective arc. And if you are able to see the weight of the arc, which is connecting hydrogen place and transition T is 2. So it means a hydrogen place must contain at least 2 number. So the two place tokens will be moved out. Similarly, 1 token will be moved out from the oxygen place. But how will be deposited? as the weight of the output arc is 2, so only 2 tokens will be deposited into the water place. So one interesting conclusion that I want to bring out over here is there is no law of conservation of tokens. Although the 3 number of tokens that are coming out from, if I sum up the number of tokens from in the input places, but only 2 tokens are deposited in the output place, and hence now it will be like this. Now that the token distribution will be 0, 1 and 2. And now you can see your transition is not enabled condition, because the hydrogen place is not containing sufficient number of tokens, although the oxygen contains, but it should be in AND logic, and hence it is a dead state. So one interesting point I can conclude here is it also helps in identification the state space of your system. How many states are possible throughout your life of a particular system, and where I want to include the term reachability graph, which basically uh, uh, which mimics all the number of possible states and the transitions that are responsible to change the state from one state to another. So if you see, okay, I'll be introducing how we can represent the reachability graph pictorially. But before that, let us understand some of the important mathematical property of the Markov chain, which says that uh, the next state of the system will only depend on the current state of the system and not on the previous states. And hence, mathematically, how we can represent this Markov property? Suppose you do have the sequence of random variable x1, x2, x3, and so on with the Markov. Then with the Markov property, you can write that the probability that my system is in n+1 state, if it is x, and it will be only depending on the probability that your system is in nth state and not on the more previous states, and hence this equation holds. Now this is a random slide just to introduce the reachability, just how we can draw the reachability graph. Suppose you do have a random figure having the 7 places, and the token distribution of the places is like M1, where M1 is written, and each places contains the token like 1 0 0 1 0 1 0, all the 7 places. And this is known as the token distribution, and which also known as the state. As I said, state is represented by the distribution of the tokens, and which we can say marking also. So one more term for the state. So here I am representing M1 for marking, and it can transit to another state by firing the transition T1, or from M2 it can lead to another state. It is just a random example, and which can be equivalently converted or transformed into the Markov chain. So all the markings are nothing but are the states, and in the Markov chain we can represent these states with the help of these circles, and the transitions, all the arcs, all the lambdas are representing the transition rate. And now let me introduce the reliability prediction framework. So uh, we have seen, now we have created a foundation which we are going to use, the concept which we are going to use in our prediction framework. So the first step includes the creation of the Petri net model that we have already seen with the help of one small example. Definitely when we will be considering the case study, we will see the Petri net model creation in that case study. Now,
Request the participants to mute their mic.
get this idea of the Excel sheet. You're already doing it. You are already doing it.
Basically, he's telling to share a Google Sheet. Huh?
There is no other way because we can't
Request
see
participants to mute their mic, please.
So the first thing is the patrinet model, and then I can convert it into the in the second phase I have to convert this patrinet model into the Markov chain, which we have already seen, and then I can use in the third phase I can use some of the mathematical concepts to compute the reliability. And so before going to the case study, let me introduce one more important mathematical concept which we are going to use. Suppose that pi it is a probability that a component is in a state I at time t, where I could be the failure states or the behavioral states as we have defined earlier. And as t goes to infinity, these probabilities converge to the stationary distribution. This is a very important statement. What does it mean? That if your system complexity is more, it will take more time to settle down. For example, suppose you fill water in a glass and you put a glass on the table. You will see like initially the water will be in zigzag position, and after some period of time it will turn down, it will settle down. And but similarly, you just replace the glass with a huge container, for example the container of the size of a room, and then you can say like it will take a very long time to settle down as compared to it was taken in the glass. So what I mean to conclude here is, as your system is more complex, it will take more time that all the probabilities will converge to the stationary distribution. And these can be computed with the help of these two equations, which are very important. The first equation is very simple. That is summation of pi I will always be 1. That states like sum of all the state probabilities of any system will be always equal to 1 at a time. And this is from the total probability law. And the second equation is also very simple. Let us explain, let's try to understand with the help of the same example. In the case of the huge container where water was filled and initially it was in a very zigzag position. For example, that state is S0. And for example, after a certain period of time, delta T, it is propagating towards more settling process, and it reaches to state S1. Then definitely the S1 will depend on the S0 into the transition probability from S0 to S1. Now further delta T time, for example, from S1 it reaches to S2. Then again S2 will depend on S1 into the transition probability from S1 to S2. And suppose after some time it reaches to the final state Sn, where it has settled down, then Sn plus 1, the next state is going to remain the same. So Sn plus 1 is equal to Sn into the transition probability from Sn to Sn plus 1. And this is what equation is. So if you see the pi estimator, which is the final state, the one more final state or next to the final state will be equal to the final state, and into the transition probability matrix. I have taken matrix because I'm considering more than one state. So these two equations will be using in our framework. Now let us consider the case study, and for example I want to give there is some safety critical system and which is having the many processing nodes which are interconnecting with IoT networks. And suppose I'm considering only two nodes. One is the embedded unit that is capturing the data from the field sensors, and it is sending that data to the display unit. So the communication protocol is very simple. For example, if I want to call a friend, I dial his number, I say hello, and when I will wait for the acknowledgement, and if I don't get the acknowledgement, I will say hello again, and I will keep on doing till I receive the acknowledgement. But I cannot wait for the infinite period of time. After a certain time, if I don't get the acknowledgement, I'll have to cut the call and I'll have to retry. So so the same concept, the same protocol has been introduced here. So whenever the embedded unit sends a new packets, the value of the count is set to 1. An embedded unit then has to wait for the acknowledgement for some period of time t1 after sending the packet. And if the embedded unit receives the acknowledgement before t1, the packet send is declared as successful, and one semaphore variable has been kept to change its complement, just to which will represent like it has been successful. And if the count is less than n and acknowledgement time not receiving any acknowledgement, or the embedded unit is not receiving any acknowledgement, it needs to transmit the packet by keeping on increasing this count variable, and otherwise the embedded unit terminates the send process unsuccessfully, where the semaphore variable will not change. And after t1 time elapsed, after the last data sent, I'll have to destroy the semaphore variable. And suppose this protocol I'll have to model using PatriNet. So this is a PatriNet figure which I explained. So there are the two places where initially the tokens are there. Interestingly, the weight of every arc is 1. I have not put any arc. So first, if the token must be first in PSRDY0, which represent that embedded unit is ready to send the packet with semaphore variable 0, and PDSR, it represents that embedded unit gets request from the display unit to send the data. And when both are ready, then the trigger TS0 will fire, which represents that embedded unit sends the packet with sequence number 0, because after I have to align the sequence number for every packet, and I have to set the retry count k is equal to 1 by firing this transition. Then PSW0, it represents a place which represents that embedded unit is waiting for the acknowledgement with sequence number 0. And if it detects the timeout for the acknowledgement, which is represented by the trigger TSW0, then acknowledgement timer timeout will be set by putting the token in the PT0N0. And then it has to retry the packet. It has to resend the packet, which is represented by the trigger TS0K, which represent that embedded unit sends the packet with sequence number, with the same sequence number, and it will keep on going till k is less than n, because up to n period n trials I'll have to do. And if it has been sent the packet successfully, which is represented by PS0S, then the trigger TCOM1 will fire, which denotes that display unit sends the acknowledgement to the embedded unit with sequence number 0. And hence acknowledgement will be received, that can be represented by putting a token in the place PR1R. And because it was waiting for the acknowledgement at PSW0, so the token will be pulled out, and again it will be ready, your system will be again ready to send the alternate packet. And now, but if your acknowledgement is not being sent not sent successfully, which is represented by the trigger of TS0ACK success, then it will transit to the place BDASU, which represent that data send is unsuccessful. So this is a failure state basically. And interestingly, this figure, the left half is a mirror image of the right half. And the reason is I have taken the 2 embedded units and 2 display units for the redundancy purpose, and for improved reliability, and every alternate packet I am sending from alternate embedded units. And it also provides the feature of the online testability. And now uh, we have to assign the parameters where the concept of the machine learning comes into the picture. You have to assign each and every transition delay. You can see like these transitions and how much time it takes. So basically for that, you'll have to build up a statistical model from the existing data or from the similar kind of projects, where you have to train that data, and so that you can it can easily predict like how much delay it will be taken from reaching the token from one place to another place. And that data, so it can be the supervised or unsupervised machine learning. And that feedback, but it is not only the machine learning, it is using the artificial neural network, because every feedback has to be passed on into the internal as an input to the neural network to improve the model. And this is what the model which gives the output, this is what the delay has been assigned in terms of seconds. And when there are the several tools which can run to give the throughput of each of the transitions, which represent the number of transitions fired per unit time. This is that value. And now we have to create the reachability graph. So for that, you have to see initially only there are the tokens in two places, and one is PSRDY0 and one is PTSR. And so you can see initially the marking was only there was the token in two markings. One is 1, then all the zeros, and then 1 0 0 0. And now after that, this transition TS0 will fire, and the tokens will be moved out and deposited to in the PSW0 and PS0S. And hence, the if you see the next marking, it can be so the tokens has been moved out from the earlier markings, and it has been deposited to the from the earlier places, and it has been deposited to the new places. And in this way we can keep on identifying the states or markings, all the possible states. And just for the easy representation, I have mapped all the lambdas from lambda 1 to lambda 12. There are the 12 transitions, which is shown in this table, right table. And now we have to create the reachability graph. So this is the this token distribution in each place, and I have shown what all the transitions that were responsible to change the state of the marking. And this is the entire reachability graph, where you can see M3 and M8 states are the failure states, because it has been transited by the unsuccessful transitions, which we have already discussed. And it can be easily transformed into the Markov chain that we have already discussed by taking a random slide. And this is the Markov chain creation, and where just all the markings have been replaced by the states. And now you have to create the generator matrix or the transition rate matrix. And just to recall, I'm going back to the same slide, just you are that so that you should be able to recall when I was discussing that how we can generate the transition rate matrix in the Markov chain. So this is what so in the transition rate matrix, we have to just write down all the states in the rows and the columns, and we have to fill in the elements of the transition rate from one state to another state. And this is the diagonal elements will be filled with the help of this formula which we have discussed, QII. So now going back to the same slide which we were discussing. So this is the transition rate, and from you can see from in the rows and in the columns we have put all the M0 to M9, and from, for example, if you see uh, in this Markov chain from M0 to M1, it is transiting with the lambda 1. From M1 to M2, it is from M1 it is transiting to M2 also, as well as M4 also, with lambda 3 and with lambda 4 transition rate. So from M0 it is transiting to M1 with lambda 1 transition rate. So the diagonal matrix, the diagonal element will be minus summation of all, and rest will be 0. And from M1 it is transiting to M2 as well as M4 with lambda 3 and lambda 4. And we can put the rest of the elements 0 other than the diagonal elements, and diagonal elements can be computed by the same formula minus summation of all the rest of the elements. And in this way we can fill in all the elements that gives a transition generator matrix or rate matrix. And now we have to find out the transition probability, which is a very simple. If I want to find out the transition probability from state I to j, I'll have to just normalize this transition from I to j, and thus I'll have to normalize this. And for normalizing, I'll have to sum all the rest of the transitions. And this will hold when j is not equal to I. If j is equal to I, all the diagonal elements will be 0. And this is the transition probability matrix. And now we have to use the same two equations where we were discussing filling the water in the large container, these two equations. So first equation was just the summation of the total probability law, where M0 plus M1 up to M9 we have to sum up, and that will give is equal to 1. And the second equation is we have used here. This is the second equation, where the final state and the previous state will be equal to same, and we have to multiply this with the transition probability matrix. And that we have now we have to solve those equations, and which can give all these values, the probability values. And we can see like M3 and M8, these are the failure states. So either we can add some of these failure states M3 and M8, and then we can subtract it by 1. So M3 plus M8, and we get subtracted by 1. That will give the quantification of the reliability of the communication module. So here I have taken only the small segment, and we have seen like what are the various parameters, and that parameters can be derived from the ML techniques or the artificial neural networks also we can use. And but your system, if your system is voluminous, you can definitely identify, you can break it down, you can decompose that system into the various components or the subsystem level, and then you can prioritize those subsystems with respect to the importance of the reliability, and at least what are the most reliable systems you can take the decision to perform such kind of analysis. So that's all I wanted to share. In case of any doubts, I'll be happy to answer.
Thank you very much, sir. There is one question in the chat box. Is P matrix useful for syndrome calculations? P matrix, is it useful for syndrome calculations?
P matrix is used for syndrome. Can you please let me know who is asking, so he can talk me to the directly, so that I can
Sure, sir. I request the participant to ask the question by unmuting.
What actually you mean, like?
Can you unmute, sir? And
Yeah, you can unmute and you can ask me. Yeah, that will be more, I think.
Hello.
Practice. Yeah.
Am I audible, sir?
Yeah, you are audible. Tell me.
So in communication systems, generally we have some coding methods, na sir,
Mm-hmm.
for coding the input information
Mm-hmm.
and transmitting, like in cryptography techniques, there like that. Can we use
Okay.
this generator matrix for syndrome calculations and so?
What do you mean by syndrome calculation? Can you please clarify?
Where we can have an errors like that.
See, as I said, when I have model this Patrinet, you are able to see like I'm trying to decompose your system into the various states, and definitely there's states comprises of behavioral states as well as failure states. So whatever the error, basically you have to treat it as the failure states, and if you are able to see the quantification method that we have taken for our case study, where M3 and M8 were the error states basically, and we had found the state probabilities of those states, and we can compute, we can subtract it by one for the quantification. So definitely it all depends on the model. See, you the Patrinet is able to capture the dynamics of your system. It all depends like how we want to model, and the modeling technique is also very much necessary to understand, because you cannot model. Modeling is not an easy. It requires a rigorous practice, and you should be able to model your system so that it can capture all the function requirement, including all the errors and all the normal states.
Okay, okay. Thank you, sir.
Yeah.
Thank you, sir. Any other questions from the participants? Okay. If there are no other questions, I take this opportunity to thank the resource person, Dr. Lalit Singh, on behalf of the participants and the organizers. Thank you very much, sir, for the detailed and informative talk.
Thank you.
I'm
Thank
sure
you
we
so
can
much.
take a lot of it from it.
Yeah.
We will share the slides also. And with that, we end this session. We will join back at 2:30. Please join back at 2:30 participants. Thank you, sir. Thank you very much.